In white box testing, we have complete access to the source code of the system that we're trying to test. And this can be great because it allows us to systematically work through the code and make sure that all of the individual parts work correctly. Right? But this can be problematic in cases where we don't have access to the source code. Right? So if you're working with proprietary code or you're working with an external web service, for instance, you can't actually see its internals, so you can't test it. One other challenge with white box testing is that there's a lot of complexity there. When you're looking at the code, there are all kinds of extra details about how everything works that can be overwhelming for a person to internalize and design good test cases for. So the best person to create test cases in a white box environment is often the developer themselves. And this can be problematic because the developer who wrote the code might systematically make errors in the tests that they create. For instance, if they've misinterpreted the spec in some important way. So an alternative to white box approaches are black box. In black box testing, we have less data available for analysis. So it really forces us to heavily leverage the specification for the code that we're trying to test to understand what the expected behaviors are supposed to be. So when we think about this, really the amount of information we have is quite limited compared to white box testing, right? We just have the specification, what's supposed to happen, and the API signature that the code is supposed to implement. Black box tests are easier for stakeholders to write who aren't the original developer. Right? So as a quality assurance person or as a tester, you can read the specification in the API signature and come up with a reasonable set of tests without being overwhelmed by all of the detail of how that code was implemented within its original implementation. Right? So hiding the extra source code from you can actually be helpful in this type of environment. So by focusing on the inputs and the outputs of the system, what we're really doing is focusing on what the system is doing, not how it was implemented. And we'll see over the next few minutes what the implications of this are, right? But it really forces us to step back and think really hard about the specification in an intentional way so that we can understand what exactly is going on within our system. Since our focus is on the inputs and outputs for our program, our aspirational goal is to exhaustively test the entire state space to make sure that our program both performs correctly for all expected and unexpected inputs. So here we have a function isValid, and all it does is take a Boolean and return a Boolean. So let's think about what inputs it can be provided. Right, so here we have input. And the only inputs that we can have here are true and false. So in this case, we can clearly see that we can exhaustively test the isValid function, and it's really no problem to do in practice. This breaks down quickly for more complex functions. So let's take a look at isGreater here. All isGreater does is it takes two numbers, a and b, and returns true if a is greater than b. It's pretty straightforward. But in this case, the state space is much larger. It's not just a couple of Booleans. Right? We're dealing with TypeScript's number type. Right? And the number in TypeScript can vary from negative 1.79 times 10 to the 308th power all the way over to 1.79 times 10 to the 308th power. Right? So this is a very large range of numbers. Right? And both a and b, the parameters a and b, can both fill this space. Right? So if we try to build this exact same table for this function, it's going to grow out of control really quickly, right? Because we're going to see something that looks like this. 0, 1, 2, 3, dot, dot, dot. And on this side of axis, we'll have 0, 1, 2, 3, dot, dot, dot. But note that these dots go all the way out to 1.79 times 10 to the 308th power. Right? And this is only the positive numbers. It also has to go down to negative 1.79 times 10 to the 308th power. So when we build out this table, we have an absolutely phenomenal number of combinations of inputs that need to be considered. Right? So what this really works out to is 1.28 times 10 to the 617th power. Right? There are a lot of options that need to be considered to exhaustively test isGreater. And this is just a function that's taking two numbers. Right? These aren't complex types. And of course, this is an absolutely humongous number. And if you try to exhaustively test this, it would never actually complete. Right? This isn't feasible in practice. So how can we deal with this kind of overload? How can we reduce the state space so that even this simple function like isGreater can be tested in a comprehensive way without resulting in this kind of state space explosion?